Thank you for the introduction. So this talk is about the interaction between machine learning models and sketches like Bloom filter. We'll see how basically they can help each other in both directions. So we will explain how these two parts can help each other. So sketches are efficient data structures with a small in memory, but they might have mistakes based on the amount of memory that they allocate. And we'll explain how they can basically enhance machine learning models by fixing some potential mistakes that the machine learning model can make. And we'll also explain how they can provide a signal we call certainty that helps to be able to understand what is the reliability level of the answer of the machine learning model. We'll also explain on the other direction how can a machine learning model can improve the accuracy of sketches like Bloom filters. Particularly, they can make some early decision before we query the sketches in order to reduce the probability for error. In particular, we will focus on a data structure from the family of a Bloom filter. The Bloom filter is a hash-based data structure based on an array that used to represent a set based on hashing elements of this array. So this data structure supports membership queries, given an element from the universe that answers whether it is part of the set, but it has false positive probability. And the false positive occurs when some elements are mapped to bits that have been set by other elements. As part of this family, there is a generalization called counting Bloom filter, which is used to represent dynamic set. So in the regular Bloom filter, you cannot delete elements. If you want to delete elements, you don't need just an array of bits, but you need to have an array of counters. Traditionally, this counting Bloom filter is just used in a similar way that the Bloom filter is used. It is support yes/no questions for the membership queries, but we use a property that actually the real values of the counters store much higher information. And the real values of the counters can actually be used to provide the certainty levels that a positive indication is correct. So if you query an element, you look at the values of the counters. If one of them is 0, the element is necessarily not inside the set with probability of 1. But if all the counters are positive, we can compute the probabilities that this indication is correct. So this is the formula on the right side here. This probability is affected by the parameters of the counting Bloom filter, like M and K, which is the memory size and the number of counters, but it also affected by a priori probability, where we denote by P, which is the a priori probability for the membership of the elements. But it is also affected by the exact values of the counters, actually by the product of these counters. Okay, so we look at some particular query of an element. We have its a priori prior probability, which is denoted by P. We look at the counter values, and then we can compute based on the CBF, the counting Bloom filter values, the prior probability that the membership is actually is correct based on these values. We see here in this slide different curves which represent different elements with different a priori probability, and we see the impact of the counter value, which is the x-axis here, on the probabilities that the indication would be correct after looking at the counting Bloom filter. And we see, for instance, that in looking at the green curve here, which represent an element with very low a priori probability, that there is a real distinction between, based on the values of the counters. For instance, we see that the membership probability after looking at the counting Bloom filter can be much higher when we see that the product of the counter is actually higher. There is a big difference based on the different values of the counting of the product of the counters here. So this information is very informative, in particular for those elements with low a priori membership probability. So this interaction between sketches and machine learning models have been presented in the past. These are two well-known combinations of these two. For instance, in the first simple known of them, we look first in the model. If it gives you a very high positive indication, you make a decision early on. But if the membership indication from the model is very low, you just go to check your Bloom filter. There is also another version where before accessing the machine learning model, you also had a first pre-filter, which is another implementation of Bloom filter. So we'll present you different architecture, which can actually be much more informative based on this additional information that we can conclude from the counting Bloom filters that cannot be given by the Bloom filter itself. So in our solution, we basically present 4 different architectures for combining these new filters with the machine learning models. There are several distinctions between of them. The first one is if we use a front stage with a Bloom filter or a counting Bloom filter. The first one, we explain what is actually the different role of the machine learning model. Either it can provide an a priori probability before accessing the machine learning model, but it can also make early decision in some of the versions here. And also the role of the counting Bloom filter would be different based on the more different models that we will show in the next slides. So these are the 2 first models that we present. The first one, in model 1, we first access the machine learning model if it gives us a very high indication that high certainty for the membership of the element, we make an early decision. But if the low indication is low enough, we just then ask and query the counting Bloom filter, and then we make a decision based on the probabilities that is given by the counting Bloom filter. And the thresholds that we use for the probability is based on our course of false positive or false negatives. In model 2, we enhance this model by eliminating some of the negative indication using the pre-filter. So before we access the machine learning model, we first access another front, which is a simple filter here, which is just a Bloom filter and not a counting Bloom filter. It makes some early decision of negative elements. Only for those with a positive indication of the first one, we access the machine learning model, and based on this probability given from the machine learning model, we use it as a prior probability, a priori probability, that for the counting Bloom filter, we said that it takes as an input the a priori probability. Here it is given by the result of the machine learning model. We also present 2 other models. The third one is actually allows you to make an early decision. So it's similar to the model number 2, but the machine learning model, if it has high certainty, you can make a positive decision before accessing the counting Bloom filter. And the fourth model is slightly more complicated. Instead of just looking at the identity of the element, it takes as an input also for the machine learning model, also the values of the counter. So as part of the training, you consider the values of the counters computed based for this particular element that are used also here. If you have this indication, if you have a low probability, you have a negative indication from the counting Bloom filter, you make a decision. If not, you access the machine learning model, and only based on this probability of the machine learning model, you access the counting Bloom filter with this as a prior probability. In the paper, we also analyze the false positive indication of the different models here. I won't go into these details here, but all these models can make both false positive and potentially also false negatives. We analyze those probabilities inside it. So if we want to summarize the different distinction between between the different models, we ask whether there is a pre-filter, whether it is a Bloom filter or another counting Bloom filter. In the first model, where the counting Bloom filter is used as a pre-filter, it can actually be the same counting Bloom filter used at the last part. So it is actually allows you saving in the memory. But in some of them, we can also make early decisions. So for instance, in model number 3, we can make early decision by the machine learning model, so the inference time can actually be shorter based on this priority. And we also ask what is actually the prior, whether the information taken from the machine learning model can be used as a prior in all the models 2, 3, and 4. We use it as a prior for the counting Bloom filter. So this is the differences between the different files. In order to make this solution practical, we also need to be able to update our models. So this is very easy to do using the counting Bloom filter. So the counting Bloom filter is able to represent dynamic sets. We can easily update the representation here, but we also need to be able to update the model. Being update the model can be slightly more expensive. So making this combination is something not trivial that we will need to consider in a potential future version of this model. So to conclude this talk, this talk is about combining machine learning model with well-known filters. with like the Bloom filter and the counting Bloom filter. The results, we call it the ability to be able to compute a probability from this light data structure like the counting Bloom filter. We refer to it as certainty, and this combination is the first one that allows you to make this combination having a non-binary indication that is only given by the Bloom filter, but by having a probability for the indications that can be correct based on the particular value, and then the ideal decision can be made based on this certainty, based on the potential cost of false positive and false negative. Thank you.
Thank you. Any questions? If no question, maybe I have a question for Professor. So if we use the learning computers, can we put it on the switch or something which is low latency and put it into the pipeline? Is that achievable? And the second question that is, I'm not sure if it can this benefit to the hash table or something, but other very important structure on the networking.
Thank you. This is a very good point. I think it's related also to the keynote we had today, earlier in the morning. So in the keynote, it was mentioned the ability to implement sketches inside switches using P4. I also personally had a chance to work on that during the postdoc I spent with Professor Jennifer Exford in Princeton University. So we have a large line of work of implementing different types of sketches, even more complicated than Bloom filter and counting Bloom filter inside the switches. And this is definitely doable. There might be cases where implementing these sketches might have trade-offs. So you, based on the constraints of the P4 language, you might have additional constraints that slightly would increase your probability of an error. But definitely this is doable and one shown. But combining this machine learning model with this new capability is something that can easily be done inside the switches.
Any more questions? No, maybe. Then we have our final speaker.
Thank you.
Thank you.